Assalamualaikum and very warm welcome to all of you. Today you are going to learn what is discrete time scaling, compression and expansion in discrete time signals, visual representation of those signals and mathematical understanding of the time scaling. So similar to the continuous time case, again that for the discrete time we say multiplying the time index by a positive scaling factor results in either compression or expansion of a signal, which is called the discrete time scaling of the signal. So let's straight away start with the graphical representation. So shown here is a signal. Anyone can tell whether it's a continuous time or discrete time signal? So you understand this is a discrete time signal because the independent variable along the x-axis is n and it has the integer value. So you understand it has value of say 1 at -2 index, at -1 it has value of 1, at 0 it has value of 3, and similarly at +1 2 and +2 1. So this is the original signal. You understand before -2 the signal in 0 and after plus 2 onwards, right? Excluding +2, that means +3 +4 +5 up to infinity, this signal is 0. So let's first see graphically. So here shown is the original signal and this is the compressed version of the signal. You understand why compressed? You see original signal is from -2 up to 2, but the this one signal, which is called the compressed signal, is from +1 up to -1 up to +1. So you see clearly this is the compressed version of the original signal, and the compressed version is this is x of n and this is x of 2n. So you understand that multiplying the time index by a positive scaling factor results in the uh, time scaling of the dt signal. Now depending upon the value of the scaling factor, which is 2 here, this signal can be compressed and this can also be expanded, right? So again shown here is the original signal x of n, and this is the expanded version of the signal. You see this is x of n and this is denoted by x of n by 2. So you see the scaling factor here is 1 by 2. So you see the resulting signal is expanded, and you can easily spot that original signal exists from uh, -2 up to +2, whereas the expanded signal exists from -4 up to +4. So hopefully it clearly gives you the idea that the original signal x of n is expanded, and in this case it's expanded by a factor of 2. So we write x of n by 2. So that this is the graphical representation for this signal. Now let's have the mathematical description for this operation. So consider the discrete time signal x of n, the same signal we have shown you. So you see at x of -3 it is equal to 0. At x of -2 it has value of 1, 2, 3 and so on, as I discussed in the previous slide. So this is the original signal, this is mathematically described here, and this is the graphical representation of this signal. So discrete time scaling concept. So for a signal xn and its time scale version, yn is given by the relationship, that is y of n is the time scale version of x of n, and y of n equals to x of a times n, where a is greater than 0. That means it's always positive. Okay, so for a discrete time signals, scaling behaves differently than we have had for the continuous time signal. In discrete time case, if a is greater than 1, there is compression similar to what we have in the continuous time case. But here the scaling factor should be integer. And if we scale a signal, for example, if we compress a signal, we basically throw away the samples which cannot be recovered normally. Okay, but in case of the continuous time signal, they are not thrown away, they are just the compressed version. So similarly, if the scaling factor is, of course, it should be positive, so it's greater than 0. And if this is less than 0, in that case, there will be expansion similar to the expansion we have in the continuous time case. But expansion introduces missing samples locations in the discrete time case. So that means normally in discrete time case, we replace those locations by 0. Whereas in the continuous time case, important thing is the first that the continuous time case, the scaling factor will be a real uh, scaling factor. That means it can have a non-integer values, but in case of discrete time, they will only have the integer values. So again, similar to the discrete continuous time case, amplitude does not change during time scaling. Only time axis changes. So here is the example case 1 where we see the compression. Okay, so again, y of n is equal to x of 2n. Y of n is the scale version of x of n, and they are related by y of n is equal to x of 2n. So that means because we are scaling it by a factor of 2, so that means only the even index samples of xn's are used. So that means y of minus 1 will be equal to x of minus 2. Now for your convenience, I have rewritten the input signal here. So x of minus 2 just has the value of 1. Similarly, then minus 1, then we have y of 0. So y of 0 is x of 0. And similarly, y of 1 will be equal to x of 2. So you see, we get only 3 samples if we scale it by a factor of 2. So the original signal had, you understand, 1, 2, right, 3, 4, 5 samples. Now they are reduced to 3. So you understand, if y of n is equal to x of 2, and that means the signal is the output signal y of n is the compressed form of the input signal. Okay, so again I have plotted the signal here, so hopefully that clarifies your concept. So again, the second case is the expansion, and that is y of n is related to x of n by y of n equals to x of n by 2. So in this case, expansion occurs, but expansion, again, keep in mind that it requires integer indices. Okay, so for odd n by 2 is not an integer. Okay, so therefore odd index samples become undefined or 0. So if we define it to be 0, so let we have the new definition, and y of n, we write y of n is equal to x of n by 2 if n is even, and if n is not even, then we write in that case 0. Okay, so again, for your convenience, I have written the values of signal here, and the resulting signal, that is the expanded version of the input signal, is plotted here. So again, if we take from the n equals to say minus 6, so y of minus 6 will be equal to x of minus 3. So at x of minus 3, signal has 0 value. So this is the resulting calculated value. So you understand, at even index values, if x of n is non-zero, then we have its values, right? So but if x of n is 0, then of course that is y of n is also 0 for that particular value of n. So for example, y of minus 3 will be equal to x of 1.5, because they are related by this one. So okay, you can easily write, right, because y of minus 3, so x and minus 3 by 2, so minus 3 by 2 is n is not even, so in that case we will replace by 0. So y of 0, then y of minus 2 will be, I replace, we understand, n by minus 2, so minus 2 divided by minus plus 2, so it will be x of minus 1. So as x of minus 1 has value of 2, so y of minus 2 will have value of 2, again y of minus 1. So because in this case n is not even, so it will be replaced by 0. Then again y is 0, so when y is 0, so uh, x of 0 by 2 is x of 0, and x of 0 has value of 3, so we have 3, and so on. So hopefully you can go through all these and you can find these values. So that ends the lecture here. To recap, in this lecture, we introduced time scaling of discrete time signals. We learned how scaling changes the time axis while preserving the amplitude. We studied compression using x of 2n, and similarly expansion using x of n by 2. You understand, for the expansion, uh, we have the missing sample values, so normally they are replaced by 0, but we can also use some other mathematical formula, say the average of the two signals, and we replace the new value by the average of the samples and so on. But maybe this is the advanced topic, so for your level it's okay that if n is even, then you replace by the value. If n is odd, in that case you write y, value of y for that odd value equals to 0. So the focus was on building intuition visually rather than memorization. So in the next lecture, we'll study continuous time signal reflection step by step, again using graphical as well as the mathematical representation, so that you have the clear understanding of that. And again, this lecture is part of Signal System Foundation course with Python. So that's all from my side. See you in the next lecture. Goodbye until then.